Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 8, 2025, about 2 days ago. The striking result is that this paper shows loss follows a power law as trained sequence length grows, while the parameter count stays fixed, and longer sequences even win on loss versus wall time. The paper is titled Recurrence-Complete Frame-Based Action Models, and the implications for model training are quite significant. Beyond that, the work argues true serial computation is necessary, defines true depth and recurrence completeness, presents synthetic diagnostics where parallel models fail, and unveils a frame-based recurrent architecture trained from Git histories. The previous discussion established why serial aggregation matters. Figure 1 illustrates strict data dependence with a forward-only jump program, where the identity of instruction T+1 remains unknown until instruction T resolves. The colored instruction list shows executed steps in green and skipped steps in red, which makes control flow inherently sequential. Because only forward references are allowed, the required true depth scales with input length. The final halt state, A or B, becomes knowable only after the entire sequence runs. Alright, Figure 1 showed why the task force's strict serial dependence. Table 1 reports transformer results on the forward referencing jumps task, with layer counts up to 8 and embedding size 256. Training accuracy stays near 1, but validation sits around 66 to 82% at max depth 4 and drops to roughly 59 to 68% at max depth 8. Adding layers barely helps, which signals overfitting and a failure to learn the required true depth. Alright, Table 1 showed weak generalization despite high training accuracy. Figure 2 shows transformer validation accuracy versus layer count, separating max depth 4 and max depth 8 with a clear legend. Accuracy rises slightly with more layers, peaking around 6 to 7 layers, then dips at 8, which suggests overfitting. The depth gap stays large, roughly 15 to 20 percentage points, so added layers do not recover the missing true depth. The pattern reinforces that time-parallel models struggle as required sequential depth grows. So Figure 2 highlighted weak gains for transformers. Figure 3 shows Mamba validation accuracy versus layer count across 3 maximum depths. The blue curve at depth 4 rises quickly and nears 1 by around 12 layers, while the red curve at depth 8 lags and only approaches the low to mid-90s with many layers. The green curve at depth 16 climbs slowly, reaching about 88% at 16 layers. Layer scaling helps, but accuracy requires proportional depth, which signals a critical sequential depth that Mamba cannot overcome efficiently. Okay, Figure 3 showed that Mamba needed more layers as depth grew. Figure 4 reports LSTM validation accuracy versus maximum depth, with a single one-layer model that stays strong across depths. Accuracy holds around 96% through depth 16, then declines gradually to about 86% at depth 32, which still surpasses the much deeper Mamba runs. The rightmost point marks that drop. The legend highlights this is a one-layer LSTM, underscoring true serial integration. Okay, Figure 4 showed strong serial generalization. Figure 18 lays out the frame-based action pipeline. The left side shows grid frames xt-1, xt, and xt+1 passed through a transformer frame head to produce per-frame embeddings. Those embeddings feed a residual stack of LSTM cells with constant error carousel and MLP blocks, which integrates over time to predict the next action. The right side contains the residual LSTM stack and action outputs, reinforcing that temporal integration is strictly serial. So 2 takeaways stand out. True serial integration matters for long horizon tasks, and a recurrence-complete design with LSTM temporal stacks scales predictably, showing power law gains with longer sequences that even amortize wall time. The implications reach coding agents and other agentic systems, nudging training and hardware toward efficient serial pipelines. Thanks for listening. I am Alex, and this was the AI Research Roundup.